So today we have Jesper Derehag here from Ericsson, old friend and colleague of mine since I was at Ericsson. It's about 1,000 years ago. But you've been in the, you've stayed in industry and you have sort of the other perspective of working on machine learning in more, perhaps more applied settings, but at least more of an engineering perspective. So it's going to be exciting to hear what you're going to say today.
All right. Thank you. I hope everybody can hear me okay. If not, let me know. And also this presentation is, the content is kind of loosely coupled and circumstantial and not very research-like. So, and the point to that is really more to keep it more interactive in some sense. So I want to encourage you to interrupt me if you have any questions, or if you want to say I'm incorrect or wrong or whatever it may be. And I think I would be happy, at least if nothing else, it would spike a discussion in terms of what the state of the field is in terms of research, but also in terms of what is actually put into production today. Because there is this big connect between, I think, machine learning research and what's actually being used in the real world. And there is this, I think it's called something like the concept valley or something like that, that every project seems to end up in some form of proof of concept project, and very rarely actually end up in production. And to me, it's really interesting to kind of figure out, why is that the case? What is it that we're doing wrong? Not only as researcher, but more generally speaking in terms of the field itself. But first, so our group is quite large at the moment. Not all of them are actually part of our group, but I and a few others here sit in a machine learning team at a department called Packet Core Systems and Technology. And we do more kind of applied research style things. So we're not a product development team, but we do more proof of concepts and more applied stuff, but also a lot of input in terms of strategy and architecture, etc. So as I said, I need to kind of rush through. So as I mentioned, this whole talk is about really the realization that when you're doing your modeling and model selection, every choice you do will have usually a pretty big impact on the downstream implementation. So that's kind of the overall theme of it, but I want to still tie it into something real and not only stand here and blab. So I have a use case where we, and this is a real production, something that is in production today. And the project itself was actually done, I think 3 or 4 years ago. So it's quite old at this point. But still, it's a very good example in the sense that it highlights a lot of the issues in a very extreme kind of way. So let's start with kind of introducing the use case. So mobility in telecommunication networks. So here we have what's called a LTE network, a 4G network. So usually when a UE or a user moves around in the network, this is represented by this car. Usually they're in something called active mode, and that means that they have fairly recently been sending packets up and down in some way or another. So that means that the radio is in active mode and the network is fully aware of exactly where the user is in the network. So the network would know that in this particular case, the car is connected to eNode B, and it used to be in eNode B1. And E node B here is just the terminology for a base station, essentially your Wi-Fi hotspot in the Wi-Fi example. So as you're moving through the network, you're doing handovers when you're in active mode. You're doing handovers between E node B1 and E node B2. I hope you can see my mouse. Yeah. So as the car is moving here, you would kind of move your connection, your session from the number 1 to the number 2. You would do a handover request, and that kind of tells the network where I am at the moment. And looking at it from a more holistic point of view, we have something called the MME, which is where this project is about. So this is the mobility management entity. And essentially the role of the MME is just to keep track of the location of the user in the network on an extremely high level. And basically, the closer and closer you get towards the internet, the fewer and fewer boxes you have, and the fewer and fewer kind of mobility-oriented tasks they tend to do. So on the far right-hand side, we have some, for instance, the P gateway, which is more for keeping track of things like how much bandwidth you've consumed, and if you're allowed to actually consume more, if you've kind of used up your quota and so on. But what we're talking about here is this mobility manager, this node that is primarily its responsibility is to keep track of where the user is in terms of the network. But the problem is that UEs, and sometimes I'm saying UE here, but what I mean is user equipment, meaning a user. The problem is that when a user has not transmitted data for a while, it goes into something called idle mode. So that means it shuts down its radio, and it's no longer reporting back to the network where it's residing, but the session itself kind of exists in the network. So the network is aware that the user is somewhere in the network, roughly speaking, in terms of its location, but it doesn't know exactly where it is. And this user could be moving around in the network quite arbitrarily in terms of where it is. But if we imagine then what happens if we get a downlink packet, let's say somebody is trying to give you a call, and the network doesn't really know which E node B you are at in terms of its location. So from a standards perspective, basically what the MME does is it sends a paging request to a group of E node Bs, essentially just asking, is this where the user is or not? And if the user is in that E node B, it will kind of wake up and send a response saying, here I am, in some sense. So the problem is sending these many paging signals, these many paging requests is obviously not very efficient. So if you have a suboptimal situation here, you will send a lot of signals and kind of send a lot of signals and thereby kind of overloading all the E node Bs in terms of how many of these paging requests they can handle and so on. So there is a direct relation to kind of how clever you can be in terms of predicting where the user is versus how loaded the network as a whole is in terms of the amount of signals it needs to send. In this particular case, we would have the user is kind of connected to E node B, so we would send 3 paging requests to kind of figure out where it is. So the product context then. So looking at the MME itself, and that's the Ericsson MME. So there are many vendors actually implementing MMEs, but ours is conceptually seen as you can see it as an embedded product. And embedded here means that it's kind of sold as a box or a standalone product, and it's also upgraded in terms of a box or a standalone product. So it's not like your typical web application where you have a number of services and you want to upgrade some small part of some service, and you can do A/B testing on that particular little service and kind of load distribute and kind of increasingly test out things in this live network. So the big difference here is that we're selling a box and we're giving it to a customer, and when we've sold it, it's out of our hands. We can't do anything. We can't interact with it. Usually they are not even connected to the internet in the sense that it would be allowed to send arbitrary traffic to some server, or even worse, going back. And I mean, that's for safety reasons. So, I mean, telecommunication networks are critical infrastructure in the sense that if it goes down, it's really, really bad for society in general. So there's a lot of kind of security consciousness in terms of what they are allowing towards the internet or not. So like the first layer of filtering obviously is not allowing these boxes to actually communicate outside their segment in the network. And as I said, also, I mean, it's sold as a standalone product, and there's kind of, when we've sold it, we can't really do anything with it as it is today, or rather as it used to be. But there's also obviously a cost in terms of maintaining that product by the operators themselves. So when they get the box and plug it in, they still need to maintain it and monitoring it and kind of make sure it's not going down in that sense. The operators are spending a lot of money actually just to make sure their networks are up and running and so on. So everything has a cost in that sense. And just for the sake of context, one MME is roughly equivalent to something like 10 blade servers in one single MME. Typically one MME can handle up to something on the order of around 1 million users. I think it's even more theoretically, but I think usually when operators dimension their networks is something around this order in terms of how many users they're actually handling simultaneously. So with a typical network, you would have something on the order of the 10 to 20 MMEs for like a national scale operator in Sweden, for instance. So obviously there is a lot of redundancy and so on here. Also, a fun fact is that the MME is implemented in Erlang for those people who enjoy languages and specifically functional languages. And also in terms of constraints here, you should be aware of that every CPU cycle or memory or network I or whatever it is that is used for machine learning. So everything we do inside these nodes for machine learning or anything else, that means that that's compute that's not used for users. So everything we do needs to be super conscious about capacity in terms of conscious about capacity in terms of kind of what we're allowed to do or not, functionally speaking. Obviously no GPUs and so on. Right. And also just as an example, we have, this is actually a cell map from Lindholmen area in Gothenburg. So I think this is the Ericsson office and the ri.se office just next to it here. So you see kind of the scale of the number of eNode Bs you would have. So this is from one operator in this area, and specifically only for eNode Bs, for LTE network. So you typically have on the order of 300, 400, 500 meters between eNode Bs like this. Also worth mentioning here, I write here that a single MME typically handles something on the order of 30,000 eNode Bs. So if we would super naively just try and find a single UE with one large tracking area covering the whole of Sweden as an example, you would need to page 30,000 eNodeBs to find one user for one single call. And these are unicast messages, so it would be a lot of messages in the absolute worst case. And also, we can look at this map and realize that there is some overlapping behavior here. So if you're going through this interstate here, for instance, it's not an interstate, but a major road, major highway, you can see that you have some overlapping in terms of coverage. So as you're going through this road, for instance, you would have coverage from both eNodeB 498 and eNodeB 481, for instance. So it's not obvious which eNodeB you would happen to connect to. It's not always the shortest path that is the only decision point. There are many things that influences which eNodeB you will end up in. Right. And in the current smart paging, the current MMEs, they have an algorithm called, or a function called smart paging. And essentially what it does is there's this kind of hand-tuned model that's been there for decades that essentially takes a stepwise approach to paging. So let's say we have this car that went idle somewhere in tracking area 1 and ended up somewhere in tracking area 2, close to eNodeB 6 here. So while it's idle, so the last observation point from the network perspective was eNodeB 1, and it has traversed a lot of places here before where we last observed it. But usually this algorithm, it works by first starting by paging the last eNodeB. So that's where it was last observed. So that would be eNodeB 1. And that's usually a very good strategy. That will give you something around 90% of the cases you have not moved anywhere. You're just staying at the same place. So whatever we do for points 2, 3, and 4 here is for the remaining like 10%, something like that. Obviously, this differs depending on time and so on, but conceptually or on average, this is the way it looks. The legacy implementation was this historical eNodeB list where they just saved like the previously visited eNodeBs that this particular user happened to go through. And the assumption here was that people are kind of moving the same ways from day to day. So you usually go to work at the same day every day, and then you go back home. And the assumption was that you're not actually moving through that many eNodeBs in reality. So by just saving this historical list, that would give you a pretty good intermediate step in terms of who to page. This is not actually true, as it turns out. People are moving through many more eNodeBs than what they can practically fit into this historical list. Remember that this list would need to be stored for every user. So there's a very big limit in terms of memory, kind of how large this list can be.
How many users would you store that information for?
Yeah, so typically it could be up towards 1 million users. So in a single node, and let's say you have an eNodeB list of 10, which is the maximum kind of the maximum length you can configure it for. So depending on the size of your, if you're having it as a U32 or whatever, or U16 or whatever you want to have, it's usually on the order of like, yeah, let's say 40 bytes per user, which doesn't sound a lot, but if it's millions of users, that kind of builds up very quickly. Right, and the last 3 and 4 steps are more from a standards perspective, where usually a user needs to let the network know if it's moving between tracking areas. So a tracking area is a grouping of eNode Bs. So if the user would move from tracking area 1 to tracking area 2, in the normal case, it would need to send a what's called a tracking area update, basically notifying the network that now I'm in this area over here. So you don't need to page everyone in tracking area 1 to find me, because now I'm in number 2 somewhere. But this is only true to a point. So they also have something called the tracking area list, basically saying that you're allowed to move within these 10 tracking areas, for instance, without doing this tracking area update. So it's not always the case that you will report when you're moving across it. So that's why they have both the 3 and the 4 steps. So either page tracking area 1 or page both tracking area 1 and tracking area 2. Yeah, so last eNode B, historical eNode B, for instance, could be something like this. Last tracking area and historical tracking area list. So that's it for the kind of context. Any questions so far? Okay, so just for the sake of argument, once again, if we look at this one, so what we want to do is implement some machine learning model that replaces step 1 and 2 in one way or another. So step 3 and 4 is kind of worst case fallback. And from a machine learning perspective or an implementation perspective, that's good actually, because that means that whatever we do, we will never catastrophically fail. We will only perform suboptimally, which is quite a nice property to have when you're doing machine learning or probabilistic style projects. Probabilistic in the sense that you're doing machine learning. So what would happen if we fail catastrophically in step 1 and 2 is just that the UE would instead be found in step 3 or 4, which would mean we would waste a lot of signals and we would have added a lot of latency because you would have to move through step 1 and 2 to get to 3 and 4. But at least you will not have catastrophically failed in the sense that you will not find the UE at all. So for the sake of argument, then if we look at these steps 1 and 2, so in the literature, and there's actually a quite surprisingly large amount of literature in terms of mobility prediction for telecommunication networks. So usually it's you can actually view it on 2 levels. So it's mobility prediction on the cell level. So they often talk about something called cell shaping, for instance. So it's more on the base station side where you want to locate some user in kind of within the coverage area of that particular eNode B or cell. And there's a lot of literature around that. And then there's more on like the network side of things where you don't know exactly which eNode B a user where it belongs. So if we look at these more on the network level side of the literature, they are usually divided into 2 different type models. So either you have network level models. So network level models essentially means that you have some model of your network topology where you don't actually care about the individual user behavior. You only care about that if a user any user is in eNode B1, they are very probable to go to eNode B2, for instance. And there are variations of this where, for instance, people have been doing clustering in terms of trying to group eNode Bs together, because oftentimes it's very hard to pinpoint exactly which eNode B it is. It's usually one out of like 2 or 3 or whatever it may be, depending on like the very spot coverage that the user happens to be in at the moment when you're trying to do the call, for instance. And then on the other side of it is that you could have user level models also. So where you're essentially, instead of modeling the network, you're modeling on the user level. Let's say some representation of a user typically goes through eNode Bs 1 and 2 on Monday mornings. Then these the representation of that user usually ends up on eNode B3, for instance. So they are contextual on the sense that they are trying to model individual user behavior rather than just modeling more on like the network behavior in general. So the models themselves are actually not that interesting. These are just examples for variations that we've tried, and we've tried about 1 billion more of these in different variations, and there also exist 1 billion more of them in the literature. So the models themselves are not that interesting, at least not for this talk, where we want to discuss using these models as like an example blueprint. Just start to reason about, if we actually would use one of these models, what does it actually mean in terms of the implementation and the deployment in this particular setting. And like I said, I'm not sure how representative this setting is for the typical machine learning project in general. But what it does is that it highlights a lot of the problems that I still feel exists in the more regular setting, although they are slightly more hidden, or you can deal with them in a slightly easier way, but they still exist. So an example model here would be, for instance, a very simple Markov chain, where you would just model more on the network level the transition probabilities that if any user has been observed last in eNode B, they would, for instance, have a 70% probability of going to eNode B2. And you can increase the order of these. So you could have, for instance, an order 2 Markov chain, where you would look at like the trajectory of the user. If it's coming from eNode B0, eNode B0 and eNode BX, you could have a very similar probability distribution if you think trajectories are important or not. And on the far, so this is a super simple model. On like the far end of the scale on the other side, it would be a recurrent neural network. In this particular case, we're modeling trajectories in terms of the previously visited eNode Bs. And we're doing it through LSTM. So we're modeling the trajectory and learning some latent representation of that trajectory. So this would still be, it's one model for the entire node, but we're learning some form of representation of a user. So it's not like it's one model per user, but we're learning some representation of that mobility. As input to that particular model as well, we could add like the top eNode Bs that this user usually resides in. So that could be their home, their eNode Bs that they have close to their home and close to their work, for instance, and the time of day. And then all of this would then output softmax probability distribution over all the eNode Bs in that network. And I would say 3, 4, 5 years ago, this would be the standard solution. If you would say do an RNN of this problem, this is probably the model you would come up with quite naively. Correct me if I'm wrong. And it's also worth mentioning that this was done 3-4 years ago. So this was pretty much at the same time as graph neural networks came about. So that's why we haven't really tested any GNNs or anything like that. But
so 3 or 4 years ago, how much? What length of the history did you use there?
32, maybe. I don't remember actually. It was like 4 years ago.
But quite a long history in comparison to the Markov chain.
Yeah. But I mean, we tried many models, but I think it was something like that. And I mean, we tweaked the history and tweaked the top ENODs and so on. And that's exactly part of this discussion. So for this particular model, you have a lot of hyperparameters that you could potentially tune. Yes. And would those hyperparameters, would they stay the same across every network? What would be your intuition?
I suppose that people, I don't know, how are people moving about?
Yeah, I mean, as an example, I mean, the examples I've given here have been very large networks, but we're also selling the same product for really, really small networks where you have like 10 ENODs in the whole network. So whatever we come up with, it needs to work in the extremely small setting and in the extremely large setting as well. But we'll get to that. I didn't mean to put you on the spot, but rather to kind of as a soft entry point to the discussion. People have also been doing a lot of other variations in terms of in our data sets, we don't have the GPS coordinates for the ENODs. So when we're looking at these data sets, we don't practically actually know where they're coming from. It's been anonymized in the sense that we don't know the country, we don't know the network, we don't know, in theory, we shouldn't know anything about it. Of course, the number of networks that has these many ENODs, there are not that many in the world that has networks of this size. So practically speaking, usually you can do a pretty good guess anyway, but so usually what other people have done and what we've done as well is you can actually do dimensionality reduction in the sense that you project the graph into a 2D space of some form, and then you hopefully end up with a map of the network such that the clusters here, you see the colors rough corresponds to the tracking areas, because the tracking areas we know, at least from an ID perspective. So these 2D projections, you could also consider models or architectures where you're, instead of trying to predict like the next ENOD, instead you're trying to predict the XY coordinates in some Euclidean space. So it could be trying to predict some XY coordinate and then just finding the closest ENOD or the closest group of ENODs to that particular XY coordinate. So there are variations of that as well. Also worth mentioning that even though in our data set we don't have the GPS coordinates for the ENODs, the MME as a network function does not have access to that either, even though of course the operator has that, but the MME function itself doesn't have that.
Question here.
Yep.
The location of ENOD, is it itself, I mean, does it come in the privacy aspect? I mean, like location of the user is privacy aspect, but I wonder if why you don't have, or you can't have access to the GPS location for the ENOD.
You were breaking up. What was the question? Why we don't have the GPS coordinates, or?
Exactly. So I mean, like, the reason that we don't have access to the GPS location of the e-node Bs? Is it because of the privacy concerns or something like?
No. So in the network function perspective, from a standardization perspective, so if we ignore kind of the issue of transferring data between from an operator to Ericsson, for instance. So if we ignore that for a moment and just look at it from a standardization perspective, the MME simply doesn't have that information what the GPS coordinates is for a e-node B. Everything the MME observes is just the e-node B ID. That's all that can be observed from like the standardized signals that goes between these. So it's more from a standardization perspective. But with that being said, of course, you could conceive of ways of kind of entering those GPS coordinates into the MME through some other means that's not standardized. You could do that theoretically. But there's, I mean, it's very common that, for instance, there would be some other vendor that actually builds the e-node Bs, and the MME is built by some third vendor. So for the MME to get the GPS coordinates from some third party that's not standardized is usually pretty unlikely. So usually it has to be standardized in one way or another, which it isn't. And with that being said, in terms of privacy, when we get the data from the operator, in this case, to do these types of studies, we anonymize the data quite thoroughly in the sense that we do want to hide exactly which e-node B it is, because you could use that information later on to implicitly determine users. So for our own sake, we also want to hide kind of as much as is practically possible any identifier in that sense. So we're hiding the e-node B ID simply because if we know the true e-node B ID, we can look it up and see that, oh, this e-node B ID is in China on this particular road, and there's this group of 5 people that happen to be living in that area. So why don't we can pretty safely assume that one of the 5 users that tends to be stationary around that point are probably the people living around there. So when we do anonymization, we try to, as much as is practically possible, anonymize and hide that, because we don't really need to have that information. Did that answer the question? Okay. So domain problem. So this is when we get to the juicy bits, and I've already wasted 40 minutes on just setting the problem. So the domain problem 1 then. So the importance, what I call the importance of evaluation. So whatever metric you choose for your task, it's super important that whatever metric you choose is a true representation of whatever task it is you're solving. So in this particular case, it would be very naive to just say that, well, paging accuracy, what about that? Just what is the percentage of accuracy of me finding a UE, a user, if I only get one chance, for instance. That would be a very poor proxy for what we want to achieve. As I said, we have the possibility of paging multiple ones. So paging one at a time is probably not a good idea. So, and also in this particular task, actually, this is a multi-objective problem in the sense that it's important both with minimizing latency, the time it takes to actually find the UE, but we also want to minimize the number of signals. So, for instance, if you have an emergency call, you would like to optimize for latency so that the phone starts ringing as quickly as possible. And there is also government kind of rules for how long that can take, is allowed to take. And in that particular case, you would be willing to sacrifice the number of signals to try and find the user as quickly as possible. But if it's a mobile broadband user, which is the majority of them, the downlink, the time it takes to wake up the UI is maybe not that interesting. So there you want to optimize for signaling instead. So there you want to find the user in some reasonable amount of time, but with as few signals as possible. So also naively, it is a multi-objective problem, but it's even more complicated than that. So like I said, optimize for latency, you could just choose to page everything at once, and you will find the UI in the first attempt, more or less. Or if you the extreme case of optimizing for signals, you could just iteratively page one after another until you find it. So that way you will have minimized on average the number of signals that you use, but at the same time you've sacrificed a lot of latency. So there is this balance. Either you're quick or you don't use a lot of signals. So given those two business objectives, so how do we actually evaluate? So like I mentioned, accuracy, AUC scores or what have you is probably a poor measurement of this. You could argue that mean reciprocal rank, which is typically used in recommender systems, essentially how many guesses do I need until I find it? That sounds reasonable in some sense. But at the same time, the mean reciprocal rank would, in its most naive form, would be the mean MRR over the whole data set. Is it true that we want to maximize MRR on average, or is it that only at a specific time or not? We could obviously also look for Pareto optimality, which would be the standard way in terms of multi-objective optimization. You could do something really simple and just create this cost product between signal times latency, and so on. And here I really want to emphasize this in terms of the engineering effort. Spending a lot of effort on this, deciding this evaluation metric is super important, because not that it will make or break your project, but it will save you a lot of time in the end, because it will force you to start to think about what is it that we're actually trying to solve. What is the fundamental problem here? Is it to get a high accuracy on ImageNet, or is it actually something else that's more important? Right. Another problem is covariate shift or dataset shift drift. In this particular case, networks are kind of dynamic. So operators are adding and removing and changing InnoDs on pretty much a daily basis. So if we go back to our models here again, and we just try this this reality on our two models, what does that actually mean? So if InnoDs are from the network are removed or added in terms of the network, what does that mean for our model? Especially if we consider the softmax here, where we have this probability distribution over all the InnoDs. So what happens if one InnoD is removed, or we need to add another InnoD? Similarly, in NLP, you would have, if you have out of vocabulary words that you all of a sudden want to predict, you usually need to retrain or fine-tune your model in one way or another. And if this happens on a daily basis, how do you actually deal with that? And also consider this in the setting of, we're selling a box. We cannot monitor it, we cannot touch it, we cannot do anything with it. When we've sold it, we're done. We can't do anything. So if you consider that, how will you actually dimension an RNN, for instance, such or build a system that has an RNN that is able to learn the dynamics of this network? even looking at the hyperparameters. So for the fully connected layer, in this particular case, they seem to use the 4096 in the first layer for whatever reason. Is that the good value for an arbitrary network with 10 eNodeBs? Probably not. That would be gross over parameterization, I think. You would probably have about 10 users as well in such a network. And also, if you consider this top eNodeB, which is quite a natural thing to add if you think about the problem itself. So your typical data scientist, and that would include me as well here. So your typical data scientist, they look at some graph and they realize that, oh, people do have some trajectories, and oh, people do tend to stay at home at night and they stay at the same ones. So if we have this historical trajectory, like we said before, if it was 32 or whatever it was, if we have that trajectory, and in terms of that vanishing gradient, if that trajectory is long enough so that you're not able to cover your home base, you need to somehow do like a skip connection in terms of what your home eNodeB is. But what does that selection actually mean in terms of the task? So how do you actually calculate the top eNodeBs for every user? You can't do that in a real live network. I mean, you would need to store every transaction or every basically transition for every user over a fairly extended period of time. And this is a lot of data. So it's just not really tractable to do that. Yeah. And also, if you consider our setting in terms of the sold it as a box, it is a box. It's a fixed machine with a fixed number of CPUs, etc. So what happens when we go to a customer and say that, well, you can buy our MME, but we also need to have this training cluster sitting right next to it, preferably with a GPU, that you need to not only transmit all the data that's generated by the MME. So in essence, you've halved the throughput of the MME itself, because everything will need to be mirrored somewhere else. And keep in mind, I think somewhere on the line of like 20 or 30% of all internet traffic goes through our products. So it's very easy to forget the volume of these things. Yeah, it grows extremely quickly in terms of data and what you need to collect and what you need to throw away. So if you need to mirror every packet, you've essentially halved your throughput in terms of number of signals. You need to store that data in one way or another, which means depending on how much data you need, we're talking probably at least terabytes of data per week, if not more, for a single MME. And if you have 10 MMEs, you're quite quickly up into the petabyte scale of things, just for a week worth of data. And the next question is, if you train that model, how will you actually transfer and deploy that model to the MME? And that in and of itself is a very big kind of topic, of course, in terms of execution environments and so on. But you realize that whatever we select in this particular setting will highly influence how we actually sell our products and what's practically feasible or not. With that being said, of course, in many situations, you maybe already have this kind of data science infrastructure already in place, so you can do more things like this. And that is kind of the model for telecommunications in general going forward. But at the time we did this, that did not exist. So we were kind of tied in terms of what we can do or not. But still, it highlights the problem of doing these super large models in any context, that it has this assumption that you have this big whole cluster of additional infrastructure, which you may or may not have, depending on your application. Right. Flexible deployment. I really need to rush through this. So we've touched upon it already. So how can an operator, when they get this box, how can actually install it so there's minimal effort on their side? So they usually don't have a data scientist sitting there understanding the parameters, understanding how to tune models, or anything like that. So if we tell them, well, you need to increase the parameters in your fully connected network to X or Y, that operator would have no idea what you're talking about. So how can you actually build a system that is flexible enough to work in a wide variety of settings? That's kind of the main gist of it. And this robustness is a big thing, I would argue. So it's not robustness in terms of the implementation itself, but rather robustness of the model. So whatever model you do, will it work in a large scale setting? Will it work in a small scale setting? When you configure it, how much tuning do you need to do, or will it just simply work or not? And so on. And also, if we would sell this to a customer, the first question that we would get back, so how much compute do we actually need for this training if we would build this system? And then all of a sudden you realize that, oh, that's kind of complicated to answer. It depends on the network, and it depends on a million different things. So this added complexity of this is maybe not tractable. And yeah, so model lifecycle management has been covered in many ways, but I think I've mentioned pretty much everything already. And another big point here is how much data is needed to get the model to actually converge, which is, from a robustness perspective, really interesting. So if you have a really small network, will it converge or not? And also the importance of debugging. And debugging here is more kind of introspection in terms of the model itself. So if your model starts to diverge from whatever evaluation metric you have, so it could diverge just by and of itself, that you actually have a covariate shift, or it could be an adversarial example where you have some user that's just moving between things. I mean, we have had an example where Google had problems with Google Maps because somebody put like a shopping cart full of cell phones and just walked down the highway, and all of a sudden there was a traffic jam. That one was quite funny, I thought. Also, fairness and bias. It's easy to think that, well, it's not really applicable in this case. But is that really true? So if we think about it, in terms of latency, I mean, there could be differences in terms of latency depending on whatever model you happen to have. If you're a user that's kind of more in the rural areas where you would have less data, your model would likely be less accurate in the kind of in the accuracy perspective of things. So that would mean that you actually have higher latency if you're let's say in a more poor area where you would have less coverage, as an example. So it's not a major concern, but you need to somehow think about it as well. Right. Model selection conclusion then. So given this prior discussion, it's quite obvious which model I would choose, I think. But so the question is, which model would you choose? So considering this evaluation score and deployment options and so on, and bear in mind, I haven't even shown you the accuracy of the models yet, but just off of the arguments we already have.
Sounds like a lot of hassle.
Yeah.
we may need to drop this project.
Yeah. But so what we started to do, and we got really happy as well when we started looking at these. I'll not go through like the evaluation score itself, but the kind of the insights we gained was that actually, if we look at the best performing model, in this case the RNN as an example, and the simplest but still somewhat functioning model, which was our Markov chain. Here it's called the order 1 Markov model. But what we learned was that empirically we realized that for this step 1 and 2 to actually gain anything in terms of the final score, it needs to be at least 80% accurate in terms of how many paging procedures that needs to be done and not end up in the later ones, because they will penalize you quite aggressively. So you need to be at least 80% accurate in step 1 and 2 jointly. So given that, it turns out actually that regardless of whatever model you're choosing, if you are allowed to recommend 10 eNode Bs or more, basically every model performs the same. So the model doesn't actually, for the downstream task, the model doesn't matter at all, actually. So that's super exciting in and of itself, because you kind of realize that, oh, all of a sudden it's not a discussion on whether it's worth doing this or not in terms of deploying an RNN and all the infrastructure needed, but it literally doesn't matter. The Markov model works just as well or as bad as any other model if you need to have an accuracy above 80%. So usually either model needs at least 5 eNode Bs, a list of at least 5 eNode Bs to perform at that level. Right, and also 1 minute. So this is an example in the end, basically how the end product looks when we have this Markov chain in place. So here we're looking at the total number of signals for the whole MME. So not only the paging, but the whole throughput of the entire node. And we can see that the Markov chain greatly outperforms the legacy smart paging procedure. And not only that, I want to highlight here that it actually performs significantly better at peak hours. So these peaks here is the peak hours. And actually, when you think about it, operators don't care what the throughput is during nighttime, because everything is idling and sleeping anyway. So there's no danger in that situation. But they do dimension their networks after peak hours. So what you really, really care about in terms of number of signals is your peak hours. And our model seems to perform quite well explicitly there. And it doesn't really matter if we are not as good during night hour, because it simply doesn't matter to the operator.
Is it relevant what the y-axis scale is here?
Not for the presentation, but of course for the customer. So I mean the number of signals.
It's a great improvement, I suppose.
Yeah. So if we, I think maybe I should have added percentages here or something. So if legacy smart paging is 100%, the Markov chain improves it with, I think, between 40 and 80% compared to legacy and optimally configured smart paging. Depending on the network. So between 40 and 80%. And depending on the network depends on how many eNode Bs they have and how they configure their tracking areas and so on. But you're right, I should have added the percentage or some form of baseline at least. Right, and also convergence here is really interesting for the sake of argument. I'm not sure how much time I have in terms of running overtime.
It's we don't have a fixed end time, but perhaps if you are able to wrap up in 5 minutes or so?
Yeah, I'll try. So
okay.
The short version is that how much the kind of one of the insights that we gained here is that you have some, if you have this model as an online model, meaning it's running inside the MME itself, we are not training it in batches. It's online. It's continuously learning. We're not doing stop and hold type approaches at all. But it's completely online. So then the question is how much data is actually needed before the model converges, because it's on immediately. We cannot, well, theoretically, we could fall back to the legacy smart paging and then after some time maybe enable the machine learning one while we've collected enough data. But we wanted to look at how much data do we actually need? How long time does it actually take before it outperforms the legacy one? And as we can see in this graph, it pretty much immediately outperforms it. But this is not true. If we zoom in this, if we use all the data exposed to the entire MME, it takes about 20 minutes before it's outperforming or before it has converged, I think. So it's in the order of minutes, which is not a big deal, really. Usually these things runs for theoretically years and years before it actually needs to restart or anything. So 20 minutes out of those years is not a big thing. So covariate shift in terms of this Markov chain. So we added this decaying factor to the Markov chain. So with some frequency, we just kind of divide the transition probabilities by half with some frequency. So that means if there are no more transitions between two nodes, eventually they will kind of move towards zero, and then we can remove them when they reach zero. So you have this natural kind of update of the model and removing of nodes, etc. It's also quite an important thing here in terms of how you choose to do this halving in terms of frequency, or if you just want to have a threshold in terms of number of signals. But once again, robustness is king. So we don't know if any network ever sends more than 10,000 signals, or if it ever sends more than 10 million signals. We don't know. So using something like number of signals is not very robust in terms of this diverse set of networks. So once again, model selection and tuning of the model with respect to the downstream task is super important. Yes, changing fixed length list in terms of the E0B list to a confidence based threshold is also quite interesting from a robustness perspective. If we, let's say you have a list length of, with the legacy thing, if you have a list length of 10 and you have some user that traverses, but we don't know if this particular network, maybe they only have stationary IoT devices. So that list length of 10 is probably pretty useless in that particular network. So that would mean if you have a fixed length, you would always page 10, regardless if those are actually adds anything or not to this particular network. So I would argue that confidence levels are more robust in the sense that they will allow the network to be more flexible. They will allow the Markov chain to be more flexible in terms of different network topologies. So if E0B only has one single neighbor, there's no point in paging 10 other E0Bs because it's just not, there's no point to it. And it turns out that these confidence levels are pretty robust across networks as well. So 98% confidence level is one of the kind of proposals we had, and that seems to be fairly robust across many, many different networks. Yes, so that was this. I don't think I have time to go through the sparse graph implementation. I'm not sure this is the correct audience to do that either. So we can do questions.
Thank you, Jesper. Do we have any questions?
Maybe I can ask a quick question. So you have. Maybe I can ask a quick question. Can you hear me?
Yeah, that's better.
The microphone was up. So I was thinking that how much these methods that you're developing can be kind of generalized to different settings. You mentioned covariate shift and so on. Do you consider this, for example, in all of the projects that you have, or how much you can generalize what you are doing?
Yeah, no, I mean, covariate shift is definitely a problem in almost all machine learning settings when you put it in production, I would say. But doing online learning, that is the extreme. I mean, for the last couple of decades, at least, I think the kind of the experience has been that never do online learning with respect to machine learning, because they always break down and you cannot control them. So at least if you do offline learning, you can at least monitor and test your model before deploying it and so on. And there is definitely arguments for why that's the case and why online learning is a bad idea. And I do agree that it is a bad idea in current state of the art in some sense. But that is kind of part of the problem, I think, is that our models are not very robust at all, even if we look at it academically. I mean, they very quickly break down and for many reasons. So, and they do tend to find these, for instance, spurious correlations for whatever your task may be, and they tend to overfit and tend to overestimate in terms of the confidence levels or softmax or whatever it may be. So
shouldn't online learning help you with the robustness issues rather than
Yes. Yeah, well, maybe help you. It depends on how robust your model is in your online setting. The problem with online learning is that you don't have a stop button. That's the problem. So when your models start to diverge, what do you do? But the kind of, for me, the fundamental problem is this robustness in terms of our models, and then we've invented all these other things to try and compensate for the lack of robustness in our models in terms of lifecycle management. So, I mean, you have things like what's it called? In Kubeflow, for instance, where you can add stuff like automatic evaluation metrics, where you kind of collect your data and train your model, and it will automatically evaluate your model towards some criteria on your live network, and it will not deploy the model until it kind of satisfies that criteria. So, I mean, there are a lot of tricks that people do to kind of compensate for this. But I still think the fundamental problem is that they are simply not robust enough, and we need, so for whatever reason, we've chosen to add this big infrastructure around it just to kind of combat that problem. And
is the solution you talked about today, is it in production?
Yes.
At the moment.
Yeah. Yeah. But one thing I guess is, I mean, it's kind of controversial, but sometimes, not every day, but sometimes I'm thinking that softmax, I don't know, I have this pet peeve with softmax. Sometimes I'm thinking that softmax has kind of set back the field at least a couple of years in some sense, because I mean, at least 5 years ago, everybody were doing softmax for everything. So people tended to do architectures that utilizes this kind of probability distribution. But in many cases, the real world is not this fixed setting where you have a predictable set of classes or predictable set of whatever you're trying to predict. So
people often have an overconfidence in the power of the softmax.
Yeah,
What
exactly.
does it do? And
Exactly. But it feels now it's kind of moving away somewhat from softmax, at least in terms of if we look at transformers and so on. I guess they're still used in a lot of computer vision tasks, but yeah.
Absolutely, yes.
Yeah. But the question is, what would have happened if people didn't think about the problems in terms of probability distributions? Would we have gotten better models in terms of lifelong learning or not? I'm not sure. Anything else?
Hello, this is Ife. I'm an industrial PhD from Ericsson Research, and I'm also here in KEH also. So my question would be like asking, could you please introduce me a bit, if there's something that you can share on the application of graph neural networks in this area? Let's say inside the PDU, how things have been going.
Specifically for graph neural networks?
Yes, exactly.
Yeah, in this particular project, we haven't tried the GNNs at all, because this was done before GNNs became a thing. Pretty much the same thing. I think the first GNN paper was in 2017 or something, right? The GNN paper.
Yes, exactly. GCN.
Yeah.
GNN, which is related. Yes.
Yeah. So this was pretty much at the same time. So we never tried it for this. But in terms of other projects in Ericsson, I haven't heard of anybody actually using it, but a lot of people want to use it and kind of play around with it, because a lot of our data tends to be graphical in nature. So I don't have anything against it. It's just I don't think I've seen that much with it yet, at least.
Thank you.
Mm-hmm.
I also find this, working with this graph neural network kind of a natural next step. It feels like it for you. Am I right?
Yes. But also for this particular task, I might add, I don't think the model will ever make a difference. Because here I think the problem is, in this particular setting, the problem is the data, actually. So there's this reason for why, if we look at this accuracy at K curve, so there's this reason, I believe, but it's just an hypothesis, that no model is ever able to get above these 80–90% accuracy or with fewer than 5 or 10 guesses, because the hypothesis is that from the MME perspective, it's not really predictable which E0B you will end up in. So the final decision of exactly which E0B it is will be determined by the coverage, how many other users happens to be in that E0B or not. And the coverage is also quite fickle, in the sense that you could step 5 meters to the left and all of a sudden you will get another E0B, just because you happen to have a different propagation in terms of the signal towards the E0B. So there is this kind of, once again, this is my hypothesis, that there is this kind of noise component to this, that it's, from the MME perspective, impossible to predict. Of course, if we would have much more fine-grained and detailed data from the radio side of the network, we could probably do more. But with the data we do have in the MME, I don't think the model will ever matter.
I'm more optimistic. I'm more optimistic than you, I think. I think we'll learn it, especially gradually it will learn that this switch happen often or not. I think it wouldn't be difficult for graph neural network, actually. But I'm optimistic. I'm not really expert on that.
Yeah. We'll see. I mean, like I said, it's quite a rich literature in terms of these mobility papers. So, and I have read a few papers around it, but yeah, I don't know. Oftentimes, sometimes they cheat and kind of add radio data to the data sets and so on. But realistically, with an MME can never use that data, so we're kind of screwed. But who knows? I haven't seen it. Haven't seen it yet, at least.
It sounds like it could be time for a challenge.
Yeah, like a hackathon challenge. You mean? Yeah.
Jesper seems to be eager.
Yeah, and it helps me also to implement it in a real application.
Yeah. But I mean, what I'm saying is that I'm not at all saying that graph neural networks is bad. I mean, there are many very good applications of GNNs. I'm just saying for this particular task, it's unlikely that it will end up in production. Let's put it like that.
All right. Do we have some more questions?
I have maybe a general question regarding, I mean, the point that you mentioned in terms of that the classes are not constant. So in your case, I mean, the InnoDB is kind of like, I mean, they can pop up and I work on the network side in Ericsson, and I mean, we have some use cases where due to this ANR and I mean, SON, InnoDBs and Cell can, I mean, they can be like, you know, come up and they disappear sometime. And then the same thing, like, you know, for instance, when you have like, you know, this kind of classification task, do you have any suggestion, like, I mean, in terms of from a modeling perspective? How, I mean, one way is like to start with, I mean, very basically we can have like a very sparse kind of like, you know, setup, and but that becomes like, you know, that has its own problems from a sparse perspective.
Yeah. I mean, I would say it's an interesting question from an architecture perspective. I haven't really thought about it in this particular context, but if we take transformers as an example, which is a very good example for this. So, I mean, historically, you would do these NLP models with some probability distribution of like the next word, of given some sentence, what's the probability of the next word, for instance. So historically, it was very often modeled as this probability distribution over all the possible words, right? But with transformers instead, they turn it sometimes into this kind of single variable output of the model instead. So instead of modeling every possible word, instead you have this query sentence, for instance, where you ask what is the probability that the next sentence is actually this sentence. So then all of a sudden it's a yes or a no output rather than this probability distribution. And that example to me showcases this kind of robustness of as language changes and your model and your data set changes, it's much easier to fine tune that network because you just need to feed it more data. You don't need to retrain it from scratch. You don't need to remove layers and retrain the final softmax layer or whatever it may be. You can just keep training it and just keep feeding it data without kind of without having to kind of do these quite aggressive changes to the model. Now, if something similar can be done with respect to paging, I mean, maybe you can do something similar instead of giving like a fixed list of, rather, instead of predicting this probability distribution over all InnoDBs, maybe you can give it a list of 10 InnoDBs. What's the probability of the UE being in one of these 10, for instance? I mean, that could be one approach to it.
Yeah. Thanks. Yeah. I'll look at it. I mean, usually the first thing that comes to mind with the transformer is like a lot of training, but I think it's worth it.
Yeah. But I mean, it's just it was just an example. So more from an architecture point of view, that instead of having this kind of fixed rigidity in terms of your output space, you allow it to be more flexible and kind of set the context from the outside rather than building it into the model. Maybe that's one way of putting it.
Yeah, no, thanks. It's a good comment.
Mm-hmm. Nothing else? I thought all of you would have jumped on the softmax comment. I remember you liked softmax a few years ago.
Like, I mean, you get certain inductive biases based on your decisions. Certainly, softmax has some nice properties for some things, but I totally agree. It's not the tool for everything.
Mm.
Any more comments on softmax, please? Sepidi suggests in the chat to start the master thesis around this.
Yeah.
Right.
Okay.
So, let's thank the speaker. Thank you, Jesper.
Sure.
And everybody, welcome back in 2 weeks. Next week we're on winter holidays, at least in Gothenburg. So no seminar next week, but the 25th.
All right. Thank you for having me.
Thank you.
Bye.